When a heat source radiates into a vacuum, the energy simply disappears into the void. However, inside an enclosure, those heat waves continuously bounce and reflect off the internal walls. To solve these problems, we have to evaluate the entire system as a whole. To obtain a unique solution in enclosure analysis, you must know the starting temperature or net heat transfer rate for every surface. Two rules apply. For insulated surfaces, net heat transfer rate is exactly 0. For black surfaces, emissivity is exactly 1. Computer models use complex radiosity equations to track these reflections, but engineers often use a more visual framework to reach the same result. The network method solves two surface enclosures by treating the space like an electrical circuit. Radiation heat transfer acts as current, driven by the temperature difference between surfaces. The heat flows through three specific resistors, two internal surface resistances, and the physical space resistance between them. This yields the master equation for net radiation transfer, calculating total heat flow by summing all three resistances. Each term in the equation's denominator maps directly to a visual resistor in the circuit diagram, covering surface properties and geometric spacing. This equation provides a universal algorithm for any two gray, diffuse, and opaque surfaces, though we can frequently simplify it further based on the shape of the enclosure. Common real-world geometries allow us to use simplified versions of the master equation to reach the same result more efficiently. In these common enclosed shapes, surface 1 cannot see itself, which means the view factor, F12, is always exactly 1. For a small object in a large cavity, the area ratio effectively becomes 0, removing a significant portion of the denominator to create equation 1337. With infinitely large parallel plates, equal surface areas allow variables to cancel out, resulting in a streamlined formula. Try deriving the formula for concentric cylinders. Use the master equation along with two geometric parameters. The area ratio equals the radius ratio, and the view factor is 1. Plugging those radius ratios directly into the resistance denominator gives us the specific simplified form shown in the third row. Success depends on correctly identifying the physical geometry so the appropriate simplified form can be applied. Consider a scenario involving concentric spheres, where the net heat transfer rate is known, but we need to find an unknown surface temperature. First, plug the known variables into the equation for spheres. Next, isolate the temperature term, and then calculate the fourth root to find the final temperature value. To solve any two-surface problem, identify the geometry, map the resistors, apply the two rules for specific surface types, and select the corresponding simplified equation. Viewing physical enclosures as logical thermal circuits provides a reliable and repeatable framework for solving these radiation exchanges.